All right, guys, we are at chapter 15 of 1212. I'm on slide 41. We're at the end of the PowerPoint where we're just working a few more practice problems. So on slide 41, there's a problem that says I have a reaction of H2 plus I2 to yield 2 HIs. It gives me the initial concentration of the hydrogen and iodine gases. They are both 0.0175 molar. And then it gives me, once equilibrium is established, the product hydrogen iodide concentration is 0.0276 molar. Based on that information, I should be able to solve for Kc. Okay? The question is asking, what is Kc? Well, anytime they give you information about the initial conditions and the equilibrium conditions, we're going to set up an ice table. So I start plugging my numbers in. Of course, I can hear the lyrics of Ice Ice Baby in my head as I write. So I'm going to have 0.0175 molar H2, 0.0175 molar I2, and then initially I have 0 HI. Okay, those are my initial conditions, but then once it reaches equilibrium, the problem told me that I have 0.0276 molar HI. With that information, I should be able to solve the table. Okay, I should be able to figure out what all the numbers are based on what I have. Okay, now first of all, if I know the HI, initial and final, I know the change. I started with 0, I ended up with 0.0276, so the amount that I gained was 0.0276. So I say plus 0.0276 in the change row. Now, as I fill in the ice table, the one row that will always follow the stoichiometry, which means the ratio of the coefficients, the row that it will always match up with that is the change. The middle row of the ice table, it's going to be a 1:1:2 ratio in this row. Okay? Now, on one side of the reaction, I'm going to subtract. On the other side, I'm going to add, because as I use reactants, I'm going to gain products. Or if I do have one that goes the other way, in case you're going to have a problem where you start with products, you work your way back to the reactants. Either way, one side will be subtraction, the other side is adding. You just have to figure out which way to go. But the numbers should match the ratios. So if it's 0.0276 here, that's I'm making 2 of these for every one of my reactants that I use. So I need to cut that value in half. This is kind of like 2x. I need to find out what x is for over here. Now, I'm not actually using x's because I have numbers. I can plug the actual numbers in instead of using a variable. So half of 0.0276 is going to be let me just divide it to be sure, 138, so 0.0138. So I'm going to subtract 0.0138 from I2 and subtract it from H2. Because the amount that I'm using of these two are going to be equal, because it's a 1:1, and it'll be half what I'm making of the HI, because that's 1:2 from either reactant to the product. Okay? At that point, now I can finish each column, 0.0175 minus 0.0138. It's going to give me the equilibrium concentration of I2. That's going to be 0.0037. And then the same thing for H2, 0.0037. And now that I have all the equilibrium concentrations, now I can set up my expression. Kc is going to equal the product, 0.0276, on top, but it's got to be squared because of the 2 in the reaction, over 0.0037 for the H2 times 0.0037 for the I2. So I'm just going to say 0.0037 squared. So at that point, I can plug it in. 0.0276 squared divided by 0.0037 squared equals, and I got the answer to be 55.6. So that is my Kc value for this reaction at this temperature. So now we'll do another problem. The next problem on slide 42. actually I'm on slide 43. Solid calcium carbonate decomposes to give solid calcium oxide and gaseous CO2. So let's write our reaction. CaCO3 solid yields CaO solid plus CO2 gas. Kp for this reaction is 0.0063. All right, now, what will the equilibrium partial pressure of CO2 be? Well, it didn't really give me, it only gave me the Kp value, it gave me no amounts for anything. Well, if I did an ice table, the initial change in equilibrium of my reactant and then both my products, something we haven't seen yet, but I know that when I write my equilibrium expression, it's going to be products over reactants. But if you remember, we said that solids and liquids don't appear as part of that expression. And if we do an ice table, the column under a solid is not going to be important because those numbers won't actually go into the expression. So I really can kind of ignore them when if I'm setting up an ice table, like figuring out what all the numbers are, I can ignore the column for any solids or liquids. I only have to worry about gases and aqueous compounds. All right, now on this one, if I think about it, I could fill out my ice table. I would really only have the one column here for CO2 that I actually have to deal with. But let's just think about what is Kp here. For this reaction, it's going to be the CO2 on top, the pressure of CO2. The CaO doesn't appear because it's solid, and then I would divide by calcium carbonate, again as a solid. So really there's nothing on the bottom. If you want to, you could say the pressure of CO2 over 1. But in reality, divide by 1 doesn't matter. So I can just say Kp equals the partial pressure of CO2. And since they gave me the Kp was 0.0063, well, that is the partial pressure of CO2 that I end up with at equilibrium. So that's the answer, 0.0063. There really wasn't any math to do on this one. It's more just about seeing the reaction, recognizing that the Kp expression is just going to be CO2, and then therefore the Kp and the CO2 have to be equal. All right, next one, last slide. I have a reaction 2A plus B yields 3C plus D. The value of K, let's assume it's probably a Kc value, is 4.6. Concentration of all species is initially 1.5. Which way will the reaction shift to reach equilibrium? So for this reaction, Kc will equal the concentration of C cubed times the concentration of D over concentration of A squared over the concentration of B. So when I do this, if I plug in all values, and actually, so that's equilibrium expression, if I want to know which way it's going to shift, I'm given initial concentrations. If I plug them in to this expression, it doesn't equal K, it actually equals Q. If I plug in a random set of numbers that are provided with the problem, but it's not the equilibrium values, it's just the initial concentrations, when I plug them in, the expression becomes a Q expression instead of a K expression. So I would plug in 1.5 cubed times 1.5. So that's going to give me 1.5 to the fourth on top. That's 1.5 cubed times 1.5. Over, on the bottom, it'll be 1.5 squared times 1.5, which will be 1.5 to the third. And if I have 1.5 to the fourth divided by 1.5 to the third, I'm going to cancel out. Everything on the bottom gets canceled. And then I take away 3 on top, so it's going to become to the first. So it's going to equal 1.5. Q equals 1.5. Now, at this point, I know that K is 4.6, so I can say that Q is less than K. So I know that the reaction, when Q is less than K, the reaction is going to shift to the left. So this reaction with these initial concentrations, the reaction is going to have a net shift to, I think I said to the left, to the right. It's going to shift to the right. Okay? Now, the problem doesn't say that we have to solve it, but it does ask us to set up the ice table. So let's go ahead and do that. Now the importance of finding Q there, now that I know the reaction is going to shift to the right, that's going to help me decide which side to add to and which side to take away from. Okay? So I've set my numbers, ice baby, 1.5, 1.5, 1.5, 1.5. I know it's going to shift to the right, so I'm going to add to this side, plus, plus. I'm going to subtract from that side. Adding to the right, subtracting from the left. Because I know it's shifting toward the right, I'm going to make more products. So my numbers, again, I don't know the values here. I don't know what my equilibrium is going to end up being, so I'm going to have to use x's. Essentially, if anything has a 1 in front of it, that's where x is going to go. Under B, I'm going to put minus x. Under the other ones, if they have a coefficient, I'm going to use the coefficient. So like every time I use x of B, I'm going to use twice as much of A, so it's going to be a 2x. Under C, it's going to be 3x. And under D, it's going to be x. So then I can summarize my values, 1.5 minus 2x. 1.5 minus x, 1.5 plus 3x, and 1.5 plus x. All right, now, that's my ice table all set up. I could go one more step. Problem doesn't ask me to. Well, it does ask to do write the equilibrium expression. So I go one more step and say, okay, Kc is going to equal concentration of C, 1.5 plus 3x cubed times D is 1.5 plus x over A is going to be 1.5 minus 2x squared over 1.5 minus x for B. So that's C times D over A times B using the exponents that are from the coefficients. Now, if you actually work this out, it would get really complicated mathematically because when we FOIL all this out, we're going to have an x to the fourth, x to the third, x squared, x, and then a non-x number. Again, that's above the level of math that we're going to do for this class, which is why on this problem, we didn't ask you to solve this because it would be too hard, but the setup of it should be pretty straightforward. If you understand how to set up an ice table and then how to take the equilibrium concentrations and plug them into the expression, that's the lesson that we wanted you to learn on this problem. All right, and I believe, yeah, that's the end of this PowerPoint, so that's the end of chapter 15. Have a good day.